Good morning to all of you. Am I audible? Am I audible?
Yes, sir.
Okay, thank you. So, very less amount of students are joined for the. Okay. So, we would be start the topic today, and maybe it is the last lecture of this unit number 4. Some numericals we would be take further in between of session of unit number 5 because both are associated units are there. Okay. So, uh, in the last lecture, we have discussed the topic of feedback in the op-amp. And we have seen that there are the four types of basically feedback, but out of that, we have to only learn the two as per our syllabus. These are the voltage series feedback, and second one is the voltage shunt feedback. So we have calculated the gain formula of voltage series feedback, but for today, again, I am just going to repeat this revise this process, how to find out the voltage gain formula a little bit quickly. We have already discussed this topic in the last lecture. In the case of this, I have also told you that voltage series feedback is also called as a non-inverting voltage feedback circuit because in this case, input signal is given to the non-inverting terminal and output signal, a fraction of output voltage you can say, is fed back to the inverting terminal. Okay, so in this case, if you have to be see the diagram, it is a diagram of the voltage series feedback. You can see here there is a two terminals as per the op-amp having. One is the non-inverting where we have applied the input voltage signal is V in, and at the inverting terminal here we have taken a one part of some amount fraction of the output through the RF, and R1 there is a voltage divided network is there, and it is applied to the inverting terminals. Okay, so as per the name, it is voltage series feedback. The first term voltage, we know that we have already learned in the unit number 2 as well. What is the meaning of these two words? So the first word, that is the voltage, it means what? It is a type of sampling. So only we can perform the voltage sampling whenever we have to be connect a parallel network or a feedback network is connected parallelly to the output port. So here you can see that it is connected parallelly to the output port. So the voltage will be fed back here. And the second word series, it means it is a type of mixing. So you can see here, it is connected to the inverting terminal, that is it is in series actually. Okay, so it is a voltage series feedback, and this is the equivalent diagram I have drawn, the block diagram of the feedback network, that how we have to be going to use here negative feedback. So for this particular circuit, and RL is a load resistor, VD is the difference voltage between inverting and non-inverting terminal. So you can see here V1 is the voltage at the non-inverting terminal, that is same as the V in, because there is no resistance or no other drop of the voltage is possible in as per the circuit diagram. And V2 is the voltage of the inverting terminal. Okay, and VF is a voltage, that is the voltage drop across R1. So we have to be going to analyze this circuitry. So when you are going to analyze the circuit, we would be found that it is a one kind of inverting amplifier. So what happens? The feedback voltage opposes the input voltage, means it would be 180-degree out of phase with respect to the input voltage, because it is a negative feedback is there. So what happens? The input voltage means feedback voltage would be opposed the input voltage. So the difference of both would be nothing but a difference voltage. V in minus Vf is your difference voltage is here. So if you have to be going to calculate the closed loop gain, so F is equal to V naught upon V in. That means if you have to be C, V naught is what? It is output voltage. It is nothing but the relationship with respect to the input terminal V1 minus V2 into A. A is the open loop gain, and V1 minus V2 is the difference voltage. So this is the generally we have to represent in this way the output voltage. And here the if you have to be go to the diagram of this voltage based feedback, V1 is nothing but your V in, and V2 is what? It is nothing but a Vf. So if you are going to calculate the value of the Vf from the circuit diagram, it is very much simple, that it is a voltage divided network is there. in the case of op-amp. And in this voltage divider network, there is a two resistors are connected. One is the R1 and another is the RF, that is coming out from the output terminal. Okay, and then it is going to the inverting terminal of the op-amp. Okay, so in this case, if you have to be see, this is your V1 and this is your V2. So what is the voltage across this R1? There is your VF. VF is what, according to potential divider rule, it is R1 upon R1 plus RF into V0. V0 would be here the act as a supply voltage, you can say, for this particular network. Okay, so in this way we have to be find out these equations. So you can give the number of equations as well. This is your equation number 1. This you consider 2 and 3, and this is on 4. Okay, and then you have to move further for finding out the other relationships. So V0 would be now A V1 minus V2. So it would be according to this relationship, it would be equation number 5 actually. So you have to be C, substitute the value of V1, that is V in, and V2, that is R1 V0 upon R1 plus RF. This is equation number 5. Now we have to be going to rearrange this equation. Means what we have to be do here, for this purpose we would be V0 is equal to A V in minus A R0 V0 upon R1 plus RF. So we have to be take this V0 plus A R1 V0 upon R1 plus RF on the left hand side, and the right hand side only this term would be remain. So when we have to be take the V0 as a common, so you would be find out it would become as 1 plus A R1 plus RF, that is your V0 is common. So you would be easily do the next equation, that is you would be find out that it would be become R1 plus RF plus AR1 upon R1 plus RF into V0. Okay, so finally we have to, from this point we have to be go to this equation. V0 is equal to what? I have directly written equation. You can do the calculation by your own by keeping the space, some space on your notebook, and you can further do the calculations. So it is very simple arithmetic equations are there. So V0 is equal to now become, it would became this would be goes into a denominator term, this would be goes into the numerator term. So finally it would be find out that how it would be happens. So in this particular equation we have given in this particular case you can see. So from this point this equation has been be derived to this V0, that would be become AR1 A into R1 plus RF into V in upon R1 plus RF plus AR1. Thus we can write that as from the equation number 1, that is V0 upon V in, AF is equal to V0 upon V in. So V0 is what? This is the equation. You can see 6. You can take this reference, equation of 1 and 6. Substitute this value upon V in. So you would be see that it would be cancel out V in. So AR1 plus RF, A into R1 plus RF upon R1 plus RF plus AR1. This is the exact value of the closed loop gain of the voltage series. Okay, so this is the exact value, and you can give the equation number also. This is equation number 7. Okay, now we have to be find some ideal value also. What is the ideal value of the closed loop gain for voltage series? So you would be find that, as we know that A is very large, open loop gain of the op-amp is very large. It is in some lakhs, 1 lakh or 2 lakhs are there. For the IC741 we have taken as a reference IC. So here you can take AR1, the product of this, to be very much larger as compared to the other term in the equation, that is R1 plus RF. So in this way you can write according to this assumption R1 plus RF plus AR1 is equivalent to AR1, because A is very much large number. So here we can write the equation for a closed loop gain, that is V0 upon V in is equal to what? 1 plus RF upon R1, because in the numerator, if you have to refer here, in the numerator denominator, this term would be neglected. This first term it would be neglected here because of this is very much larger. So only A would be cancelled out, R1 plus RF upon R1, that is 1 plus RF upon R1. This is also generally a gain of non-inverting amplifier as well. Okay, so this is the ideal equation, you can say, for the voltage gain. You can give the equation number 8 as well. Now we can see that we can also correlate this gain equation, the gain of feedback circuit, it is through the gain of feedback circuit, that is B, and it is the ratio of Vf upon V naught. So when you have to be calculate the feedback circuit gain B, that would become as inverted version of this AF, means R1 upon R1 plus RS. Okay, so it is a very important relationship we have got, that closed loop gain would be now become equal to or equivalent to, you can say, 1 upon V ideally. Means you can see here the closed loop gain of the voltage series amplifier would be become independent of the circuit, you can say the gain of the open loop factor and the other circuit parameter. It would be only depend upon the feedback circuit gain. Okay, so in this way we have to be correlate the closed loop gain. So there are the three equations I have written, that is one is for the ideal condition and one is for the exact condition. You can further modify the equation number 7, that is the exact equation we have learned by dividing R1 plus RF to the numerator and denominator, and you would be find out that we have just taken there, you can see the numerator we have divided R1 plus RF, and in the denominator the same. So it would be modify the new equation, and this equation number would be now equation number 10. Okay, so you can see here now it would be become, it is, you can say it is again an exact equation. So equation number 7 and 10 both are representing the exact equation. It is simpler form of that equation number 7. So you can say AF, it would be become A upon 1 plus AB. So A is what? Open loop gain. Okay, and B is the feedback circuit gain. So it would be become looking a function of open loop gain as the feedback circuit gain. But as usually the open loop gain is very large, so AB would be also very much large as compared to 1. And if you would be do so, you can again back to the equation number 9, means AF would be equivalent to the 1 upon B. So again we have to be see that this equation would be king, that overall voltage gain of the circuit equals to the reciprocal of the feedback gain. It means what? It means that closed loop gain is no longer dependent upon the open loop gain of the op amp. It would be only depend upon the feedback circuit. Okay, so the feedback gain B can be precisely controlled by adjusting the value of the voltage divider network R1 and RF, and your gain would be become independent of the amplifier. Okay, only it would be depend upon the feedback network. So whatever I have discussed till means your gain would be become independent of the amplifier, and it would be only depend upon the feedback network. So physically what is happening in the circuit? If you have to be think a question, what is actually going on in the circuit? So you would find out that the gain is approximately constant, even though the differential input voltage VD would be changes, V1 minus V2 would be changed, but still the gain is constant, closed loop gain. Means that suppose open loop gain A increases for some reasons, maybe because of temperature or some other external factors. Then what happens? The output voltage will be also try to increase. Obviously, when the A would be increased, your output voltage would be also try to increase. This means that more voltage, more amount of voltage would be fed back through the feedback network into the inverting terminal of this voltage series amplifier. And if the more amount of voltage would be feedback to the inverting terminal, means it would be result in decrease in the value of the VD. Okay, VD is what? V in minus VF. If VF would be increases, means VD would be decreases. Okay, if VD would be decreases, then what happens? Again, it would be a very important factor for deciding the output voltage V0. V0 is what? A into VD. So if VD would be decreased, means its result would be again V0 would be decreased. In again V0 would be decreased, means this is the cycle actually. So it would be completely offset the attempted gain or increase in the output voltage. Okay. So what is the benefit of the feedback is here, negative feedback is there, that whatever the gain is increase of the amplifier, it would be increase the output voltage, but again the output voltage is feeding back to the inverting terminal. Because of that, what happens? Again, it would be offsetting the increased value of the output voltage. In this way, it would be balancing the gain. Okay, so gain is here stabilized, and this is also happening on the reverse manner as well. Means if the A is decreases again, the output voltage would be decreased, and this decreased voltage of the output would be fed back to the inverting terminal, and again it would be result in the decrease of the it would be result in the decrease in the VF. If VF would be decreased, means differential voltage would be increased, and if differential voltage would be increased, it would be again increase the output voltage. In this way, again the gain is stabilized. So in the both cases, either you would be increase the open loop gain or decrease the open loop gain, your overall gain of the closed loop amplifier would be stabilized. So this is the one of the most important benefit of the negative feedback. Okay. Now we have to be again elaborate the same case with using the differential input voltage ideally 0. We have to assume that differential input voltage would be 0 ideally. So if we would be consider this, so as per the equation of output voltage, V naught is equal to what? AD into VD, we know that, or A into VD. And you can write that VD is equal to what? Output voltage upon open loop gain. And we know that the open loop gain A is very large, means ideally infinite. Physically, practically it is very large value, maybe in lakhs of the value. So what happens if you have to be refer this equation? According to this equation, what if AD is nearly or approach to the infinity, so means VD would be approach to the 0. Okay, and if VD is 0 means VD is what? V1 minus V2. And if VD is 0 means what? V1 minus V2 would be 0. V1 minus V2 is equal to 0 means V1 is equal to V2. This is the ideal condition. This says that the voltage and non-inverting terminal of an op-amp is approximately equal to the that of at the inverting terminal, provided only that open loop gain should be large. And this concept is very much useful for analyzing the closed loop op-amp circuits. We have to see the use of this particular assumption in the further analysis. Okay. So you can see that how this is possible by through these equations. Ideally closed loop voltage gain, again you can calculate that V1 is equal to V in, V2 is equal to Vf, R1 is equal to R1 upon R1 plus Rf into V0, that we have already discussed 2 or 3 slides before. And here we have assumed that V1 is equal to what? V2. Ideally we have to be assumed this is, if it is so means Vf is equal to become V in. So V in is equal to now R1 upon R1 plus Rf into V0. So you can write the V0 is equal to R1 plus Rf upon R1 means 1 plus Rf upon R1 into V. Again, you have to see that by doing this way also we have reached to the same equation that we have already written in the equation number 10. So in either of the way you can go, reach to the same condition. Okay. So the second parameter that we have to be calculate is the input resistance in the case of voltage series feedback. So this is the equivalent circuit. You please everyone draw this or take the screenshot, whatever is suitable to you. So we have to be see that here using this equivalent circuitry of the op-amp using voltage series feedback amplifier, you would be find out the Ri and RIF. Ri is what? Input resistance of the op-amp, and RIF is the input resistance of the op-amp with feedback. Okay, so here the same circuitry has been be shown. This V in is applied to the non-inverting terminal, V1 is here, and V2 is the voltage of the inverting terminal, and we have applied a feedback to the RF and R1. VF is the voltage drop across R1, but we have to be also show that internally there is an input resistance exists between these two terminals, inverting and non-inverting, that is Ri. This is the modification we have done in this particular previous circuitry. and once the current I in is flowing into the op amp. And we have also drawn the equivalent circuitry of the output network as well, that we have shown that there is some arbitrary. So you can see here we have connected it to the AVD. There's a voltage source as output network, and then there is the R0 is the equivalent output resistance of this op amp. Okay, so in this way we can also perform this, find out the input resistance. Okay, now I hope all of you have drawn this diagram. So we have to move for the further mathematical analysis. So when you have to go for this mathematical analysis, you have to find that in this circuitry, if you have to see, Ri is the input resistance or open loop resistance of the op amp, and Rif is the input resistance with feedback. Okay, so you can calculate the Rif is what? That is V in upon I in. Okay, so V in is equal to what? Vd plus Vf. We know that what is the Vd? Vd is V1 minus V2. Okay, we know general phenomena. Vd is equal to V1 minus V2. That is V1 is V in and V2 is your Vf. So Vf V in would be equal to what? Vf plus Vd. Okay, so that is mentioned here, and we know that Vf is what? It is V into V0, feedback factor gain into the output voltage. So V into V0 is what? AVD, as per our connections and equations previously we have written. So V in would become now Vd would be taken common, 1 plus AB. Okay, so 1 plus AB into Vd is what? If you have to refer this circuitry, so what is the Vd? In terms of current, we have to see that Vd is equal to I in into R in, the current flowing through the input resistance. Okay, so here we have to substitute the same value. Okay, so you would be found that V in is equal to now 1 plus AB into I in into Ri. Ri is the input resistance without feedback. So you have to just bring the I in into the denominator of the LHS side. So it would become V in upon I in, that is nothing but your Rif. Okay, is equal to Ri into 1 plus AB. Okay, so Ri into 1 plus AB. So what it means that we know that the product of A into B, A is the open loop gain and B is your feedback gain. It is much larger than the 1. It means what? Rif is much larger than the Ri, and Rif is ideally infinite, approaches to infinity, and this amplifier would become just like an ideal voltage amplifier, because Rif is approaches to infinity. You can say it is just like an ideal voltage amplifier. So in the case of voltage series amplifier, we know that input impedance with feedback would be always increases or larger as compared to the resistance without feedback, and would be improved by the factor of 1 plus A. Okay, now we have to calculate the output resistance with feedback. So this is the circuitry for the output resistance with feedback. If you have to refer the circuitry figure 6 for the calculation of input resistance and this output resistance, these are some changes we have done. First of all, we have grounded the non-inverting terminal. We have to V in has been shorted, so it would be considered as a V1. The non-inverting terminal voltage is ground or 0 volt, because we are calculating the output resistance. So we have to connected one output voltage source at the output network, that is called as a V0. From there is a one current is flowing, that is I0 is there, and this current is reached when this will be reached to this node, that is called the node name is given as N. It would be divided into the two parts. One is into the amplifier, that is IA, and another is into the feedback network, that is called the IB. Okay, IB is flowing here. So in this way, this is some modification we have to be done for the calculation of the output resistance. Okay, now with using this circuitry, we have to calculate the output resistance. So for that we have to first apply the KCL at this node N. That would be I naught would be equal to IA plus IB. Okay, so that is we have mentioned here. Whatever the modification we have done, we have just written. Okay, so R naught F is what? Here you can define the R naught F, that is equal to V naught upon I naught, that is equation number 1. Then we have to apply the KCL on this node N, and it would become I naught is equal to I naught is equal to IA plus IB. This is you can write as a equation number 2. And then since R naught is very small as compared to the RF plus R1 parallel RI, so you can assume that IA is very much larger than IB. How this is, you can see from the diagram. What I am saying, RF plus R1 parallel RI is very much larger than the R naught. See, in this particular circuitry, there is a two branches of the current. One is into the amplifier, that is IA, that is flowing into the R naught. Another is IB, that is flowing through the RF, R1, and through this network up to the RI. Okay. So if you have to be see from this end, from output to input side, not look from input to output side. We have to be now looking from output end to the input side. So you can find out that it would become an equivalent circuit, that is RF plus R1 parallel. R1 is parallel because you can say there is a one resistance only RI is connected between this node and the ground. R1 parallel RI. So this is the network would be formed here. This is the network through which IB is flowing. Okay, and we know that according to Ohm's law, if the voltage drop across these two networks would be balanced, so it would be IA into R naught. It should be IB into this resistance. Okay, so what happens on this particular case, if it is not possible that IA and IB both are same because the value of resistance is different. So if it is very much larger, RF plus R1 plus parallel RI, that means IB become smaller. And if it is R0 is smaller, means IA would become larger to balance this equation. Okay. So using the same phenomena, you would be found out that R1 RF plus R1 parallel RI, it is very much larger as compared to the R0. That means IA is very much larger as compared to the IB. And if it is so, you can assume that I0 would be equivalent to the IA because IA is very much larger. We can say that I0 is equivalent to the IA. Okay, this is equation number 3. Now we have to be see that apply the KVL on this output loop only. We have to apply the KVL is here. So when you apply the KVL on this network, we have only considering the one network that is consist of the R0 now. So according to that, if you have to be find out this, so you have to just apply the KVL on this network, start from this and end to this. So you would be found out that equation would be become V0 minus IA into R0 minus AVD. Okay, that is mentioned here, V0 minus I0 R0 minus AVD. Okay, is equal to 0. Then I0 R0 is equal to V0 minus AVD, means I0 is equal to V0 minus AVD. Okay, so in this way you can write the equation of I0 is here, that is equation number 4. Okay, then once the I0 is calculated, you have to just substitute in the equation number 1 that R0 F is equal to V0 upon I0, and you would be got this value of the output resistance with feedback. So you can see here, first of all we have written the equation of VD, that is V1 minus V2. As per our circuit connection, V1 is connected to ground, so it is 0, and V2 is nothing but the feedback voltage. So VD would be equal to become minus VF. Here VD is equal to minus VF, and VF we have already find out in the previous equation at R1 upon R1 plus RF into V0. That means VD is equal to minus V0. This is your equation number if you remember, equation number 5. So this is your equation number 5 is here. Then substitute the value of BD in the I naught equation or equation number 4. So you would be got I naught is equal to V naught plus A VD. Instead of VD, you can write the minus B V naught. So it would be V naught plus A B V naught upon R naught. V naught would be and substitute this value, this is equation number 6 now, into the equation number 1. So from equation number 1, you have to be find out that is R naught F is equal to V naught upon I naught. So substitute the value of I naught is here. You would be got R naught F is equal to become R naught upon 1 plus AB. This is very important relationship. So you can see that in the case of voltage series feedback, your output resistance with feedback would be reduced by the factor of 1 plus AB. And we know that you can say here AB is very much larger than 1. So you can see that it would become R naught upon AB also. So in this way, we have reduced here in the voltage series feedback amplifier using op amp, your output resistance has been reduced by the factor of 1 plus AB. It means it would become smaller as compared to the output resistance without feedback. Okay, so this is the general property of the voltage series feedback. Also, we know that, and that's why we know that 1 plus AB is very large value. So you can say that R naught would be R naught F would be become very smaller, or ideally it is actually 0. Now the another parameter is the bandwidth with feedback. So if you have to be consider the bandwidth with feedback, so the bandwidth of the amplifier is generally defined as the band of frequency for which gain remains constant. Here in the diagram figure 8, we would be show that the relationship between the open loop gain versus frequency curve for 741 IC op amp. And in this curve, you can see that the gain is 2 lakhs. Open loop gain of the amplifier is op amp is 2 lakhs near about. And for it would be this gain is valid for the bandwidth when it is having the 5 hertz only. And on the other hand, you can also write that unity gain bandwidth, that is when the gain is become 1, your bandwidth would be become equal to 1 megahertz. So as the gain increases, bandwidth of maximum frequency would be decreases, and as the gain decreases, your bandwidth would be increases, and that is represented as a gain bandwidth product. That is always a constant parameter. Okay, so either of the factor is increased, other factor would be decreased to balance the equation. The frequency at which the unity gain is there, that is called the unity gain bandwidth, and it is the maximum frequency of the op amp for which we are get the unity gain. So you can see from this particular diagram, the gain, maximum gain is achieved here, that is nearly the 2 lakhs, and that would be start to decrease as we would be increasing the frequency on the x-axis. Okay, and also the cut-in frequencies are also mentioned here. That is coming out nearly to the 5 to 10 hertz, and unity gain would be achieved when you are getting the frequency of 1 megahertz. Okay, this is the unity gain is there when you are to be getting the 1 megahertz frequency. So at the 1 megahertz frequency, the gain of the amplifier would be decreased to the 1. So if you have to be see that gain bandwidth product, as we have discussed, that it is a very it is a constant parameter, and higher the gain would be responsible for the smaller the bandwidth, and higher the bandwidth would be responsible for the smaller the gain. So if you are using here in the voltage feedback, we are using actually the negative feedback, and your gain our gain is actually decreasing by the factor of 1 plus AB. We have already calculated this. That means what? The closed loop gain, if it is decreases by 1 plus AB, means its bandwidth would be increased by the factor of 1 plus AB. So here you can directly write it as bandwidth with feedback is equal to 1 plus AB into bandwidth without feedback. Okay. So in this case, you can write the bandwidth equation like F, capital F, that is bandwidth of the voltage series feedback, that is f naught into 1 plus AB. This is the bandwidth without feedback. This is the bandwidth with feedback. Okay. So this is also very important relationship for the case of voltage series amplifier. Okay. So note down this equation. So this is the bandwidth equation is here. Okay. So start to fill up your attendance. We would be stop here. In the next lecture, we would be continue the voltage shunt feedback, and it is a small topic. Then we have to be start the another unit. From some last 5 minutes, the screen has not shared. You have not informed to me. Okay. Uh, quickly fill up your attendance. Time is less, and this is maybe a last lecture before Diwali. So we would meet after Diwali. So wish you all of you very happy Diwali.
Thank you, sir.
Okay. And you can refer the notes on the YouTube lectures on my YouTube channel as well. And I would be post today the assignment number 4. So try to complete this assignment within this week of the vacation for the Diwali vacation. I will be post on the classroom for the that is based on the unit number 4. I mean this unit. Okay, still some students are remaining. Please quickly fill up your attendance.